That's what we're going to look at today. Has to do with the characteristics of polynomials and particularly what we can tell from their equations. Now, I'm going to do a little bit of lead-in here, trying to find some things that are relevant that tie to these concepts. And in this case, the lead-in has to do more with like modeling of polynomials, which is a huge application of them. There is obviously an algebraic origin to polynomials as well, but here we're going to focus more on why we would be interested in understanding the characteristics of polynomials from a modeling standpoint, okay? So what I ended up finding was an article that talked about educators creating a safer place for LGBTQ students in their classroom. And I have a link to the article there if you want to go ahead and check it out. But what I found on the article was a couple of interesting graphs, and that's kind of where I want to show you how, if we understood what polynomials that are modeling, we could help answer some questions. So just to kind of do the little lead in here, it says a typical American classroom can be a place of learning and great friendship and social support. It can also be a place where bullying, ostracizing, and peer pressure turns into school day to a nightmare, especially if a student is perceived as somehow different from the norm. For students who identify as lesbian, gay, bisexual, transgender, or questioning, there's a greater risk of experiencing stigma, bullying, and prejudice during at school. And this can lead to a higher risk of mental health disorders, and that's very well documented. And there's lots of research out there dealing with this particular issue. And so as youth professionals, it's important for teachers and all youth professionals to understand what LGBTQ kids face at school and how you can help create a safe space and a supportive place for them in their classroom. So, like I said, this is a very known issue, and this should be kind of an issue that everyone's aware of. And you probably know someone who's directly affected by this issue. So what I wanted to look at was these two graphs. One of them talks about the frequency of school victimization based on sexual orientation and gender expression over time. And so you can see that they gathered data from 2001 up to 2017. And this particular data is actually promising if you notice that the trend is actually going down. Keep in mind that, as often the case in terms of reported data, it's usually underreported. So, you know, even though we're seeing this be less than 10%, that again is probably not accurate in terms of the real amount of this stuff that's going on. It's just how much is being reported. The other cool thing that they looked at was over the same amount of time, the availability of LGBTQ related school resources. And so you can see that as the resources were going up, the reported instances were going down. Now, we got to be really careful with this kind of stuff because it doesn't imply causation. It doesn't imply that the reason this trend is happening is because of this trend is happening, but it certainly is interesting. It does imply correlation, which means that as we do see that there seems to be, as this goes up, this goes down. Whether or not one or the other is causing each other to behave that way is a totally different question. But what I would ask you is, when you look at this data, what are some of the questions that you have, and how could you go about finding answers to them? And so what you would notice is that these graphs, what we would hope to do is fit a model to them. And it's pretty evident that these things are not just lines. They're not linear in nature, right? I mean, there are portions of them that seem relatively linear, but they do also have curves to them. And so that's where we get into the idea of looking at different polynomials than just linear polynomials. And again, if you understand the characteristics of them, then it can help you make predictions. So for example, what I might want to know is, what are these graphs going to do in 2018? That would be a pretty valuable question, right? Some other things I might want to know is, like, what was the specific data in 2010? You can see how we're actually missing that, right? And if I can model this well using a polynomial that I'm aware of, I can make those predictions, or I can at least try to make those predictions, right? I think one of the cool things when you look at these two lines in particular, or these two segments in particular, is that this one seems to be flattened out, but it was clearly on a downward trend. So one thing I might be interested in is this a turning point? Am I expecting this to go back upward? And this one itself is heading back upward. And so a question would be like, wow, am I expecting that to turn back downward? And so on and so forth. So Understanding these characteristics can help us to make those predictions. It can also help us to pick a model. So, we're going to get into this in a second, but for example, if this was a function such that its end behavior, if you will, curved back up, would that be a good model to model this data with? And the answer would be no, because it's unlikely, or at least we would hope it's unlikely, that this data is going to curve back up at the end. So that would be the difference in me, deciding that if I was going to use this data to predict outside of 2017, I wouldn't be picking what's called a function with even degree. I wouldn't be picking something where the end behavior headed back up this way. I would choose a function knowingly that this should continue to head downward at least. Okay? And so that's some of the conversations you can have when you get into modeling. And when you look at your learning target, the conversation I'm having with you now is just trying to impress upon you the importance of polynomials and their characteristics. So the next thing we want to do is to look at how can we infer the characteristics of a polynomial from its equation. So we're going to go a little bit more to abstract things. So I have a note here saying, although modeling data using polynomials is certainly not their only application, it's a powerful one. And using functions to make predictions is a common practice of analysis. It's helpful to be able to infer the characteristics of a function from its equation instead of always having to graph it. And by looking for patterns in the graphs and their functions, we can easily identify some common characteristics. So the families that we're going to look at in this video are constant functions, linear functions, quadratic functions, and cubic functions. And we're going to do this primarily through Desmos graphing software. And the things that we want to kind of keep in mind are the standard equation of a constant function. And then we're just going to go through this range of topics here. So we're going to look at the degree, the y-intercept, the potential number of x-intercepts, the end behavior, the potential number of turning points, the domain, and the range. And again, the goal of this lesson is not to determine these things from the actual graph. The goal of this lesson is to be able to determine these things from just looking at the equation, or at least figuring out how much of these things we can determine from the equation. So to start off, if we consider what is the standard function of a constant function, the standard constant function I can just write as y equals a, where a belongs to real numbers. So another way of thinking of that is that it is y equals a times x to the 0, but nobody bothers to do that because x to the 0 is in fact 1. The only reason I bring that up is that when you get asked what the degree, which is the highest power of x in a function, of a constant function is, well, its degree is 0. Okay? Now, in terms of its y-intercept, if we go over to Desmos and we take a look at this thing, I have one here for us. So you can see the red line, and currently I have it as y equals 0. Now that's probably the most interesting case of all constant functions, but just to mess around, I'm just going to bring that up a little bit. So you notice now that our function is y equals 1.7. And if you look at our y-intercept, we're getting 0 and 1.7. That's not a shocker. It's a horizontal line, and its y value is fixed, so that it's always going to cross at whatever that y value is fixed at. So again, if I was to take this and drag it down to negative 1.7, I would get the same idea, but negative, okay? So in terms of y-intercepts, that's what we're gonna end up getting. Now, the one kind of cool conversation with this function is that more often than not, I suppose, it does not have any x-intercepts. However, when it does have an x-intercept, it technically has infinite x-intercepts, and that is when it is actually y equals to 0 and is modeling the x-axis. So, every case other than y equals 0 will have no x-intercepts. The case of y equaling 0 will actually have infinite x-intercepts. So let's go back to our table and input that. So our y-intercept in this case, and again, we're saying for a function y equals a, our function is going to be 0 and a, or our y-intercept will be 0 and a. So as a concrete example, if I had, say, y equals 2, my y-intercept would be 0 and 2. If I had an example y equals -5, my y-intercept would be 0 and -5. So it's going to cross wherever that fixed value is held. Okay? Potential number of x-intercepts, it's always none, basically. Sorry about that school bell. It's always none, with the exception that if you have y equals 0, technically it's infinite. Sorry, this pen is not the best. Technically, there are infinite x-intercepts. That's a very unique case. Okay. In terms of the end behavior, if we look at it, if the value of a is positive, so if we go up to y equals 3, for example, its end behavior is moving from quadrant 2 to quadrant 1. And if that a value becomes negative, so if we move down here, it's going from 3 to 4. So hopefully you're seeing that it's finishing on the same, starting and finishing on the same side of the x-axis, as in above or below, all right? If it's below the x-axis, it stays below it. If it's above it, it stays above it. So for us, we can tell what its end behavior is going to be just by telling if the value of a is positive or negative. So if we think about the function again, we're saying y equals a. If a is greater than 0, that end behavior is going to be q2 to q1. And if a is less than 0, we are going to say that it is q3 to q4. And hopefully some of you out there are pretty keen, and you're going to ask me, well, what happens if it's y equals 0? And truthfully, I don't know the answer. I would assume that that's one of those mathematical things that's highly debated, but I don't truthfully know the answer as to what you would consider the end behavior to be there. So I'm going to avoid that and let you research that and figure it out and let me know. So if we go into potential number of turning points, it's pretty clear that this thing is linear. It's a horizontal line. And so there are no turning points. In terms of the domain, it continues infinitely in both directions, and therefore we can get all x values. So we're going to say x belongs to real numbers. And in terms of its range, because y is being held to one fixed value, again, if we're saying that the line is y equals a, that is its actual range. So I don't know how you want to write that, but you can literally just write y equals a, such that y belongs to real numbers, and that would be just fine. That is your range. It's that one value a. That's it. It's the only way you can get it. So I'm just going to take a snippet of the graph here and just pop it, and maybe we'll put a y equals 3 in there again. And I'll just take a quick snippet of that graph just so we have an example of what this looks like. But again, the goal here was that you're able to tell what this thing will look like from its equation and not from its graph. So the idea being here is you wouldn't have seen this graph. You would just have the equation y equals a. Okay? So the next family we want to look at are linear functions. And so linear functions for us, when you were in earlier grades, you probably saw it listed as y equals mx plus b, your slope-intercept form. But we're trying to get in the habit of looking at polynomials in a bigger picture. So we're going to always write our lead coefficient as a in this case. So for us, we're going to call it ax plus b. All right? Typically, you would have saw an n there. All right? And a and b also both belong to real numbers in this case. Okay? So in terms of degree, well, we can see that the highest power on x is 1. So this is a degree 1. From previous grades, hopefully, you've come across the fact that the b value here is in fact your y-intercept, so your constant value is your y-intercept. So for us, that's going to be 0 and b if we're working with this function. So just again to give you a concrete example here, an inductive example, if I had y equals 2x plus 1, I'd have a y-intercept 1. If I had y equals -3x, and you notice that you don't see a b value, that indicates it must be 0, and so you would have 0, 0. So that's kind of a unique situation. Now, when we talk about x-intercepts, I don't think we need to spend a whole lot of time looking at the graph of a linear function. You can see I have one right here. So the a value controls the slope as to whether it is positive or negative, and in terms of what that's going to change in our table, it's only changing the end behavior. So I'll mention this now, and we'll just include it later, but if you notice, anytime it's a negative slope, we have a decreasing function, and it heads to opposite. I guess I should say, I don't know if I can use the word opposite, but I'm going to opposite corners, let's say. So it's going to go from Q2 to Q4. If that a value is positive, we'll see this thing going from Q3 to Q1, okay? And so a is just controlling that slope. So if we just fix this as a positive function for a second, we'll make the slope 4, and we look at what b does, and I'm not sure, maybe I can. I wonder if I just click on the coordinate and let this roll. It doesn't. I was hoping it would show you it changing. But rest assured, whatever I set b to, in this case it's 3.77, that ends up giving me my y-intercept, okay? Now, the other thing is, because this thing has opposite end behaviors or opposite corner end behaviors, it will always have an x-intercept. So if we come back to our table, and we look at potential number of x-intercepts, there's no potential about it. A linear function will always have one x-intercept, okay? In terms of the end behavior, like I said, a is what dictates that, right? So if a is greater than 0, the end behavior of the linear function will be an increasing function. It'll head from Q3 to Q1. And if a is less than 0, then this is a decreasing function, and it's coming down from Q2 over to Q4. So again, the lead coefficient is what's dictating it to you. In terms of the number of turning points, again, it's a linear function, so there are no turning points. It's never going to have any. Its domain is x belongs to real numbers, and that's going to be the case for all these polynomials until we hit contextual problems, word problems. That's what we're going to get in terms of a domain. And the range, because this also continues indefinitely up and down as it travels, this will also be y belongs to real numbers. Okay. And so again, the idea, I'm going to snip it, a little picture of a linear function in here, but you should have been able to tell all of this stuff from just the equation. And again, in terms of what you're really looking for, your y-intercept is your constant value. Your end behavior is determined by your lead coefficient. And other than that, everything's pretty automatic. So I'll just snip a quick picture of this. Let's pop something with a bit of color there. Just as an example. And we'll leave that there for notes. Okay, so the next thing we want to look at are quadratic functions. And so the standard form of a quadratic function, which you may have bumped into in a previous course as well, is going to be y equals ax squared plus bx plus c. Now, there are other forms of a quadratic function. There's a factored form. Sometimes it's referred to in vertex form. We're explicitly looking at standard form in this particular case. So there's a few things we can pick out right away. What's the highest power of x on this? That would be its degree. Well, you can see the highest power on x is 2. So it's a second degree function. In terms of the y-intercept, if you think about what a y-intercept means, it always happens at x equals 0. You can't cross the y-axis without x being 0. So if you stuck 0 in for these x's, this entire front end of this function would be turned to 0. And what are you going to end up being left with? You're going to be left with c, which is why you're going to see this reoccurring thing where the y-intercept, when you have something in standard form, is just your constant. So in this case, it's 0c. So if we were to take a couple of concrete examples, let's just say negative 2x squared plus 7x minus 3, this would have a y-intercept of 0 and negative 3. Okay? Now, interesting stuff can happen with quadratics in terms of the number of x-intercepts they can cause, all right? So depending on the function, and I do have them in Desmo, so I can create them, but they're difficult to create on command at a standard form. So if I turn on my quadratic here, you'll notice I'm using different letters than I had posted. That's just because of the software. Don't worry too much about that. But what I want you to notice is that currently, this quadratic has no x-intercepts. And so that's very possible. It is possible to have a quadratic that does not have any x-intercepts. What I'm going to change is the value of the lead coefficient. I know that it says C here, but just think of it as A. I'm going to change that value, and I want you to watch what happens. When C becomes negative, this quadratic opens downward. And so you can see that now this quadratic has 2 x-intercepts. So far we know it's possible to get 0 x-intercepts, and we know it's possible to get 2 x-intercepts. Now, if I was to play around with D, that's not going to let me do it, maybe F. Again, it's a little difficult to create it, but there we go. What I'm trying to do is show you that if we had the right combination of values, we could create a situation. This is not it, they're just really close together, but we could create a situation where the vertex was on the x-axis and this only had 1 x-intercept. You can get into a really kind of interesting conversation in terms of roots of the quadratic function, roots of the quadratic equation, zeros of the function, and you can talk about double roots and double zeros and stuff, but in my mind, an x-intercept is simply the graphic display, and there's only 1 x-intercept on this particular graph at that point. So when we think about the possible number of x-intercepts of a quadratic, we know that it can have 0, it can have 1, or it can have 2, okay? The end behavior, once again, is always determined by the lead coefficient being positive or negative. So what we want to kind of think about here is as C becomes positive, our quadratic goes from, and positive is typically viewed as the standard, right? You're thinking, when you think of like Zamama quadratic, you would think of it being a positive lead coefficient. And in that case, it's coming down from Q2 and going up to Q1, right? Hopefully you can remember the conversation we had about the constant function and how I said it stayed on the same side of the x-axis. This is the same thing, right? Both of those functions are what we would call even degree functions. And so their end behaviors are going to be adjacent. They're going to be in adjacent quadrants. So it's coming down from 2 and going up to 1. If I let that C become negative, what you're going to see is that the quadrants are still adjacent, but now it's coming up from 3 and down to 4. And so with even degree functions, you're always going to find that end behavior. The end behaviors are always adjacent. With odd degree functions, the end behaviors are always non-adjacent quadrants. So if we come back to our table, our end behavior, if A, again, I'm going to say A being the lead coefficient, if A is positive, the quadratic is opening upward, and so it's going to come from Q2 and go to Q1. If A is negative, it's going to come from Q3 and go to Q4. And by the way, I'm saying come from, that's just the North American reading left to right kind of thing. Truthfully, it's however you want to frame it. These are the quadrants that the function terminates in, or doesn't even terminate in, it just travels off to, I guess would be a better way of saying it. Now, when we talk about quadratics, they all have 1 turning point. So the second you know that this thing is a quadratic from its function, you know it has 1 turning point, and that turning point is known as the vertex of the quadratic. Again, as with the other polynomials, it's going to be x belongs to real numbers. Now, the range is a little tricky, right? Because the range is the possible y values, and that's going to be dependent upon the vertex, all right? So I want you to assume for a second that the vertex is at, well, let's say h and k. That's your typical way of representing the vertex. And let's say that A is greater than 0, which means this thing is opening upward. If we have a quadratic that's opening upward, we find them. We have a quadratic that's opening upward, and its vertex is here. Think about what your range has to be. It's going to be all of the numbers greater than or equal to that range value. So in this case, it's negative 2.51. My range would be y is greater than or equal to negative 2.51. So what I'm going to do is state, if this was opening upwards, it would be y is greater than or equal to k. Now, the difference is, if it was opening downwards, which means a was negative, this sign would just switch. It would be a maximum as a vertex, and we would have to say that y is less than or equal to k. And so those are the general things you should be able to pick up on. Now, the range, like I said, some of these things you're not going to be able to distinctly see from the equation. You could know from the equation whether it opens upward or downward and know whether or not it has a maximum or minimum, but you would have to do some algebra or use technology to find that k value, okay? So just one quick snippet of this quadratic. Check that in your notes. And we'll move on to our last function. Okay. And so here's our cubic functions. Functions, our standard equation is going to look like y equals ax cubed plus bx squared plus cx plus d. Okay, so we've got 3 different coefficients and 1 constant term. The degree, again, comes from the highest power of x, so there's no big deal. I'm saying our degree is going to be 3. In terms of the y-intercept, again, this is where x is equal to 0, so any term with an x in it is going to get wiped out when we substitute in 0 for x. And so we'll be left with just 0 and d in terms of our y-intercept. So, you know, again, with another example, if I said x cubed, even if I said something like this, minus 4, it doesn't have to have middle terms. You would know that this is the constant term, or the d value, and so you could say that 0 and minus 4, sorry, it's written very poorly, 0 and minus 4 would be our y-intercept. So in terms of the potential number of x-intercepts, with cubics, we've got kind of an interesting scenario on the go. So let's jump over to Desmos for a second. And I changed the coefficients to match the ones we have in our things. Now, truthfully, you're only going to ever care about A and D in terms of this, in terms of telling stuff from the interior coefficients. But the C and the B play a role in how this thing behaves, and particularly how many x-intercepts it has, okay? So I'm going to actually get rid of C and B, because they're going to cause more confusion than they're worth. And what I'll do is I'll actually wipe out these two, so that we just kind of have the standard cubic, all right? Now, if you look at this cubic, it currently only has 1 x-intercept. And in terms of the other odd degree function we looked at, which was linear functions, remember that if its lead coefficient was positive, it went from Q3 to Q1. And if its lead coefficient was negative, it went to Q2 to Q4. That's the same thing you're going to see with a cubic as well. So again, it has that non-adjacent end behavior. And if A is positive, it's going 3 to 1. And if A is negative, it's going 2 to 4. So whenever something has that non-adjacent end behavior, it's guaranteed to have at least 1 x-intercept, all right? The interesting thing with cubics is what else we can force to happen. So I can put values in. I'm not really sure how to make this happen off the top of my head. I could show you a different factored form of a cubic and make this happen easily. But let's even take a look at this shape right here. I want you to envision me taking this shape, and if I was to start to bring this whole shape downward, okay? And imagine I brought it downward to the point where this local minimum touched that axis. Then what you would end up with is an x-intercept here and an x-intercept somewhere over here, okay? And so in that case, if I was able to just take that whole shape and bring it down, then I would be able to create two x-intercepts. So not only can you have a cubic with one x-intercept, you can also have a cubic with two x-intercepts. And then even more common than that is if I was to drop this down further, I can create a cubic with three x-intercepts. And so cubics can actually have one, two, or three x-intercepts. What they can't do though, like quadratics can, is have none. They have to at least have one x-intercept. And that's kind of, again, a characteristic of odd degree functions and even degree functions, is you can start to generalize those. So when we talk about the potential number of x-intercepts on this function, we're going to say that it has to have one, it could have two, and it could have three. When we talk about its end behavior, again, if a is greater than 0, the same as the other odd degree function, the linear function, it's going to go q3 to q1. If a is less than 0, it's going to go q2 to q4. When we talk about the number of turning points, so, and this is actually a really interesting conversation as well. Looking at this particular cubic here, we have two turning points. So we know that's possible. The other thing that's possible, and I'm just going to show you this in Desmos very quickly, is if we take, for example, what I refer to as the mama cubic, the cubic that all other cubics came from. There's your simplest possible cubic. This thing has a spot where it flattens out, but it actually doesn't have a turning point. In order for you to have a turning point, your slope has to go from either positive to negative or negative to positive. And because this thing flattens out but doesn't actually go to a place where it tends downward, this is not technically a turning point. So this particular cubic can actually have no turning points. That's kind of a cool conversation to have. So in terms of potential number of turning points for cubic, it's either 0 or 2. The domain, as we mentioned with the other polynomials, is x belongs to real numbers. And because this thing has that non-adjacent end behavior, its range is also real numbers. You know it's going to cover all of the values of y. Okay? And so there's kind of the synopsis of those families of functions. And again, the goal being you should be able to tell those features, or at least many of them, with the exception of the range of the quadratic. You should be able to tell many of the features just by looking at the equations, okay? So I want to try and leave you with one more kind of contextual reason as to why we might care about recognizing functions' behaviors. And I wanted you to look at this set of data. So what we have here are the COVID deaths by region, and these are average daily deaths per million people, right? Again, here's the citation for this. And this is basically, it was called Coronavirus Today, Graphing the Pandemic, is the article that I found. But if you look at this, I'm hoping you can see some different polynomials within this, or if you had to model this. So for example, taking a look at this function, right? We're seeing something. Oh, sorry, I just got a little bit glitched there. And I have no idea how to explain what's going on right now. But the idea being, like, you should start to look at some of these patterns and see, like, oh, wait a minute, I think that this portion here really looks cubic. So if I wanted to model and make predictions within this range, I could use a cubic regression model. I could try and make this thing match cubic, right? If you were particularly interested in maybe just the dip that happened from May up to November, you might model this section with a quadratic, right? And really, What you can also start to do is think about like why end behavior is so important in these things, because end behavior is what's going to allow you to predict what's going to happen after things go off the map, after they go off this graph. What is the end behavior of this going to be? Like if I can identify what kind of function this thing is, maybe I can make a decent prediction about its end behavior. Now, that stuff is really difficult to do for the record. Just to give you an example, had this particular survey stopped or had this data stopped in what looks to be like mid-April, then someone might think like, oh my God, look at where this graph is going. It looks like everybody's going to die eventually, right? Like, and you can make a bad prediction based off that. So you also have to take in common sense when you're doing regression models using polynomials. And that's, again, why if you understood the difference between the end behavior of an odd degree function or an even degree function, that can help you to select a better model or recognize when your extrapolation or your predictions outside of your data are going to be more meaningful or less meaningful. So hopefully that lesson helped. We'll see you next time.